Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. Now let's just get started on our set of questions for today's session. Okay, so question 1 asks, what are the main group elements? Okay, so the main group elements can be found in the S and P blocks on the periodic table. So this includes groups 1, 2, and then groups 13 to 18. Let me show what that looks like. If we pull up the periodic table, so the main group elements would be hydrogen, lithium, sodium, and all the way down. So the alkali metals, and then the alkali metals such as beryllium, magnesium, calcium, and so on, not including the noble gases, but also the P blocks. So carbon, nitrogen, oxygen, fluorine as well. And the junior tutor said that the main group elements or the representative elements are any elements in the periodic table that belong to the S and P blocks, which comprise elements in groups 1 and 2 and groups 13 to 18. Yep, so the solution is correct. Okay, so question number 2. Using the Vesper model, the molecular geometry of the central atom in phosphorus trichloride is linear, trigonoplanar, tetrahedral, bent, or trigonal pyramidal. Okay, so to answer this question, we first need to draw out the Lewis structure for phosphorus trichloride. So we need to calculate the total number of valence electrons that are in this molecule. So phosphorus has 5 valence electrons and chlorine has 7. And since there are 3 chlorine atoms, we multiply this by 3. And when we add these values up, we get a total of 26 valence electrons. So now let's try to draw out the skeletal structure of PCl3. So phosphorus will be our central atom since it is the least electronegative, and we can form 3 single bonds to chlorine. And from here, I'll also draw in all of the lone pairs that can be found on chlorine as well. So if we recall that each bond contains 2 bonding electrons, and we have 3 bonds, and we can see that each chlorine atom contains 6 non-bonding electrons. So far, I have drawn 24 out of the 26 electrons in this structure. So for the remaining 2, I'm just going to place them on my phosphorus atom. So now I have the Lewis structure for phosphorus trichloride, and I need to find out its molecular geometry. So if we analyze the central atom, we'll see that the phosphorus contains one lone pair, and it has 3 bonded atoms. So if I use a Vesper table, I can find out its molecular shape. Okay, so when a molecule has one lone pair and 3 bonded atoms, it has a trigonal pyramid molecular shape. And also, its electron geometry would be considered tetrahedral. Okay, so if we look at our phosphorus atom, it is sp3 hybridized, and the bond angles between all of the charge clouds would be 109.5 degrees. Okay, so let's see what the junior tutor said. If we look at all our different options, then I guess we would see that option E is our correct answer. And the junior tutor said, in order to know the molecular geometry of a compound, the Lewis structure must be drawn first. Applying the Vesper model, the most stable structure of a compound is the form wherein the least repulsion can be observed. So there's a central P atom, and the chlorine atoms are connected to it. There are 5 valence electrons, wherein 3 of them can be used to share electrons with the chlorine atoms that would need only 1 more electron to abide by the octet rule. And then they drew out the structure. And since the central phosphorus has a lone pair, all of the chlorine atoms are pushed to the opposite side. This resulted in the structure in the figure above and forms a trigonal pyramid as its molecular geometry. Thus the letter is E. Yep. So the solution is correct. Okay, so question number 3 says the molar mass of potassium iodide, Ki, is 166 grams per mole. How many grams of potassium iodide must be added to 250 milliliter volumetric flask to prepare a solution that is 0.1 mole per liter in potassium iodide? Okay, so let's write down everything that we know. We know that the molar mass of potassium iodide is 166 grams per mole. So if this value wasn't given, then we would just look at our periodic table, find the molar masses of potassium and iodine, and then add them together. And we know the volume of the solution is 200 milliliters. And to convert to liters, we just need to multiply this by the conversion factor, where 1 liter is equal to 1,000 milliliters. So if we divide 250 by 1,000, we get 0.25 liters of solution. We also know our desired concentration, which is 0.1 moles per liter. So this is why I converted my volume to liters, just so that everything is in the same values. Okay, so now that I have everything that's given, we need to calculate for mass, but the first step is to find the number of moles of potassium iodide. Okay, so we know concentration and we also know the volume. So if we recall that concentration is equal to number of moles divided by volume, then we can rearrange this equation to solve for N. Okay, so number of moles is equal to concentration times volume. And we know our concentration is 0.1 moles per liter. And we know our volume is 0.25 liters. So if we multiply the two, our liters will cancel out. And our number of moles is equal to 0.025. Okay, so step 2 is to then find the mass of potassium iodide needed for this solution. So if we recall that the number of moles is equal to mass over molar mass, we can rearrange this equation to solve for mass. So the number of moles is what we found in the previous step. It was 0.025 moles. And the molar mass was already given to us. It was 166.00 grams per mole. So now if we multiply the two, our moles will cancel out. And the number of grams we get is 4.15 grams. And this is the mass of potassium iodide we need to prepare a solution that is 0.1 moles per liter in a 250 volumetric flask. Okay, so the junior tutor said the same thing, find the number of moles. They got 0.025 by multiplying concentration and volume. And then they calculated for mass by multiplying the number of moles by the molar mass. So this solution is correct. Okay, so question number 4. Write plausible Lewis structures for A, formic acid, and B, acetaldehyde. Okay, so let's do formic acid first. Which is HCOOH. And to write out its Lewis structure, we first need to calculate the total number of valence electrons in this compound. So we know that carbon has 4 valence electrons, hydrogen has 1, and there are 2 hydrogen atoms, so we multiply this by 2. And oxygen contains 6. And again, since there are 2 oxygen atoms, we multiply that by 2. And we get a total number of electrons equal to 18. So now let's try to draw out our skeletal structure. So carbon is most likely our central atom. And I'm just going to draw single bonds to 2 oxygens and 1 of the hydrogens. And then I'm also going to make one of my oxygens bonded to the second hydrogen. So now I have this skeletal structure here. And if we look at the octet of carbon, it doesn't have a full octet yet. And there's only 3 bonds to the carbon. So since carbon prefers to have 4 bonds in total, I'm just going to make this top oxygen have a double bond. So now if I wanted to find out how many electrons I've drawn so far, I'm going to count how many bonds we have. So we have 5 bonds, and each of these bonds contains 2 bonding electrons. So I only have 10 out of the 18 electrons drawn so far. So for the remaining 8, I can place them as lone pairs on both of my oxygen atoms. Okay, so this is the Lewis structure for formic acid. And now let's do the same thing for acetaldehyde, which is CH3CHO. Okay, so let's also start off by finding its total number of valence electrons. Carbons is 4, and we have 2 carbon atoms this time, so we multiply that by 2. Hydrogen is 1, multiply that by 4, and oxygen's is 6. So if we add all these electrons up, we also get 18 valence electrons. So now let's also try to draw its skeletal structure. We have the 2 carbons, and one of the carbons will be single bonded to 3 hydrogens, and the other one will be bonded to a hydrogen and another oxygen. So again, if we look at our second carbon, you can see that there is only 3 bonds to it, and carbon prefers to have 4. So I'm just going to make this a double bond. And if I count out how many electrons I've drawn so far, I have 7 bonds, so 14 electrons out of the 18. So for the remaining 4, I will place them on my oxygen. And this is the Lewis structure for acetaldehyde. So now let's see what the junior tutor said. Part A is to determine the total number of valence electrons for this molecule. So for carbon, there was 4, oxygen, they showed the math and got 12, and 2, and when they added it up, they got 18. So this structure uses up 8 electrons, 2 electrons for each single bond of the 18 valence electrons. So this leaves 10 more electrons available. Place these 10 electrons as lone pairs on the oxygen atoms to complete the octet. So then they noticed that carbon doesn't have a complete octet yet, so they brought one of those pairs of electrons down to form a double bond between that carbon and the oxygen. Okay, so they got the same Lewis structure. And then for part B, they also got 18 electrons. And the skeletal structure doesn't seem to be showing up, but they still kind of explained correctly what the answer should be. So I'm just going to say this solution is correct. And then in brackets, there may be some issue in loading final answer. Okay, so question number 5. How many valence electrons does an electrically neutral calcium atom have? Okay, so when finding out the valence electrons, It first helps to look at a periodic table to see what group it's in. Since sometimes, oh, this one doesn't even have the group names. Because sometimes the group number can tell us how many electrons are in, how many valence electrons are in that atom. One's cut out. Might be good. So it's kind of small, but if you can see here, calcium is in group 2. Group 2A. So therefore, it has 2 valence electrons. So another way that we can visualize this is by drawing out an atom of calcium. So let's find out its atomic number. So calcium has the atomic number of 20. Which means that it has 12 protons. And if we have 12 protons, oh, sorry, 20. And if we have 20 protons and a neutral calcium atom, that means we also have 20 electrons. So now if we try to sketch out an atom of calcium, we can show that its inner ring will have 2 electrons. And then the next ring will have 8. And then the next ring will have another 8. So this is only 18 out of the 20. So for the valence shell, it'll have the last 2 valence electrons. Okay, so the junior tutor said that, oh wait, I didn't look at the options yet. So therefore option number C. And junior tutor said that calcium is a group 2A element. Group 2A elements have 2 valence electrons in their outermost shell. In order to verify this, let's determine the number of protons in the neutral calcium atom. Calcium has an atomic number equal to 20, so its atomic number is equal to the number of protons. Thus, calcium contains 20 protons inside its nucleus, and they drew out its electron configuration. So since 4s is the highest and outermost energy shell of calcium, it contains 2 electrons. So therefore the correct answer is C. Yep, so this solution is correct. Okay, so question number 6. What is the molar mass of C12H22O11? Okay, so to find the molar mass of this compound, we need to find the individual molar masses of each of these atoms. And to do that, we'll use the periodic table. We also need to take into account how many of each atom are in this compound, just so that we can multiply that molar mass by the superscripts. For example, we have 12 atoms of carbon in this compound, so we multiply the molar mass of carbon by 12, and we're going to add 22 times the molar mass of hydrogen, plus 11 times the molar mass of oxygen. So now let's plug in their values. Carbon has a molar mass of 12.01 grams per mole. Hydrogen has a molar mass of 1.01 grams per mole. And finally, oxygen has a molar mass of around 16 grams per mole. So now if we add these values up, we get 342.34 grams per mole for this compound. And the junior tutor said that the molar mass of a compound is the total molar mass of individual elements in the chemical formula. The subscripts in the chemical formula indicate the number of the same elements present in the compound. This will be used to multiply the molar mass of that certain atom since it is part of the compound. Thus, the molar mass is 342.34. So this solution is correct. Okay, so question number 7 is, what is the electron configuration of selenium beyond its noble gas core? Okay, so when writing out the electron configuration, we need to follow certain steps. So the first step is to divide our periodic table into the different orbital sections. So for example, S, P, D, and F. So typically in a chemistry exam, you're given a periodic table, so it's important if you know how to divide it into these orbital sections. So let's look up what that might look like. Okay, so this is the periodic table broken up into the sections. So the S block are the first two columns here, including helium. And the P block is this green section, ranging from boron to the noble gases. The D block are these transition metals. And finally, the F block are the last two rows, the lactanides and actinides. So after dividing your periodic table into the different sections, starting from hydrogen, we move left to right across the periodic table and from there we would write the row number followed by the block letter. And also we show how many electrons we have in each orbital using superscripts. I'll also add as a note for part 2 that when we get to block D, we write the row number -1. And when we get to the F block, we write the row number -2. Okay, so let's look at our example which I believe was selenium. And they ask for selenium beyond its noble gas core, but it just helps if we write out the full electron configuration and then find out what the noble gas core is, and then we can find out our answer. Okay, so let's find selenium on the periodic table. You can see it's right here, atomic number 21. So starting from hydrogen, I'm going to write the row number, which is 1, and then the block letter, which is S, and then to show how many electrons can be in the s orbital, we use the superscript. So only 2 electrons can fit in an s orbital, so this is the max. So we write 1s2. And you can see that this corresponds to hydrogen and helium's electron configurations. Okay, so on to the next row. We write 2, s, and then 2. Moving over to the p orbital, we're still in row 2. And a p orbital can hold a maximum of 6 electrons. So its superscript will be 6. And then we move on to the next row, which is the 3s orbital. 3s2, and then 3p6. And then we write 4s2. Thought this was selenium, but I think it's Sc. Selenium's actually here, atomic number 34. So we have to keep on going. 4s2, and then 3d10. And then we're back at 4p. And we just need to count out how many electrons until we get up to our desired element, which is the selenium. So it's 1, 2, 3, 4. So it ends up in 4p4. So this is the full electron configuration of selenium. So if we wanted to write this in the shorthand configuration, we look at the noble gas that comes before selenium, which is argon, and we put the argon in square brackets, like so. And then from there, we continue to write the remaining electron configuration like normal. So argon 4s2, 3d10, and then 4p4. So now if we look at what the question asks, the electron configuration beyond its noble gas core, you can see that it is option C. So sometimes you can write the d orbital having a lower energy than the s orbital, like they did in the question. So they have 3d10, and then 4s2, and then 4p4. So this is because for some transition metals, the d orbital is lower in energy than the 4s orbital. Okay, so let's see what the junior tutor said. Let's write the electron configuration of selenium. They have 1s2, 2s2, 2p6, 3s3. I think they mean 3s2, 3p6, 3d10, yeah, 4s2, and then 4p4. Okay, so they said the noble gas preceding selenium is argon, and they summed up the electron configuration of argon. Again, this should be 3s2. They wrote the shorthand configuration of selenium. Thus, choice C is the configuration. So this solution is correct. And then I'm just going to put in brackets that the s orbitals should only hold a maximum of 2 electrons. So for example, it should be 3s2 instead of 3s3. Okay, so I'm just adding that extra note, but they still got the correct answer and the correct explanation. So this solution is still correct. Okay, so question number 8 is to write the complete electron configuration of krypton using the periodic table. Express your answer in complete form in order of increasing orbital. So again, we need to write an electron configuration. And the first step is to divide our periodic table into the different sections. So we have the S block, which are the first two columns here. The P block is shown in green. And the D block are the middle transition metals. And the F block are the last two rows, the lactanides and actinides. So let's find krypton on the periodic table. You can see that it is one of the noble gases. And starting from hydrogen, we move left to right across the periodic table, writing the row number followed by the block letter. So I have the rules written here. So once we get to the D block, we write the row number -1, and then once we get to the F block, we write the row number -2. And then we can show how many electrons are in each orbital using superscripts. So let's look at krypton. Its atomic number is 36, so starting from hydrogen, I write the row number, which is 1, the block letter, which is S, and then to show how many electrons can fit in the 1s orbital, we put the superscript of 2. So a maximum of 2 electrons is able to fit in the s orbital. So moving down to the next row, we write row 2, block letter S, and again, only 2 electrons can fit here. Then when we move across, we go to the p orbital. So row 2, block letter is P, and the p orbitals can hold a maximum of 6 electrons. So we can write 2p6. Next row is 3s2. Moving over, we write 3p6. And then 4s2. And then once we get to the D block, you'll notice that the row number is -1. So instead of row 4, we write row 3, D, and the D block is able to hold a maximum of 10 electrons. So we write 3d10, and then we move across to 4p, and krypton is at the very end, so we write 4p6. So now if we see what the junior tutor said, they said that krypton has an atomic number of 36. We then use the periodic table below as a guide in writing the electron configuration. Okay, so this this periodic table, it's kind of hard to read, but it's pretty helpful because they write out all of their electron configurations and how they end off. So this is interesting. But you'll notice that with the transition metals, they wrote the 4s1 orbital coming before the 3d orbital. So sometimes, well, most of the times with transition metals, our 4s orbital would actually be lower than our 3d orbital. So we sometimes have to be careful with that, especially when we have to remove electrons or add electrons because, for example, if we had like copper plus and we removed an electron, we wouldn't remove an electron from the 3d10 orbital, we would remove it from the 4s1 orbital. So you just have to kind of be careful in writing the orders of your electron configuration. But anyways, the junior tutor said electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, and they wrote 3d10 first, so this is also what I mean. It can be lower in energy than the 4s orbital. And then they wrote 4s2 and then 4p6. Okay, so this solution is correct. Okay, so those are all the questions for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you enjoyed today's video, you can give it a thumbs up and a comment, or you can share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.